In this video, we're going to take a look at how to solve inequalities that have logarithms in them. So you can see the question here. We've got this inequality and there's two logarithms, and it's very confusing to look at, and you might be kind of stuck on where to begin with something like this. Well, the first thing that you should try to do with questions like these is you want to get rid of the logarithms, or try to simplify the logarithms in some way. So we can see that since we've got two different logarithms here, the best place that we would start would be try to combine these logarithms into one expression using the properties that we know of logarithms. So let's move things over. So we've got log base 2 of x over x minus 3, and then we're adding log 2 of 1 minus x, and this is going to be greater than 1. So now you can see a little bit more clearly, and you might need a refresher in the properties of logarithms here. But if we have two logarithms with the same base and we're adding them together, well, that's the same thing as just multiplying the insides of the logarithms together in a single logarithm of the same base. So this term would then become log base 2 of, now we've got x over x minus 3 times 1 minus x. And this is all greater than 1. So this is not too bad so far. Simplified things a little bit. So now, like I said, we want to get rid of the logarithm, right? So one way that we can get rid of a logarithm is by raising everything to the exponent of the same base of the logarithm, right? Because here, if we have log base 2, then if that is 2 to the power of log base 2 of something, well then since log base 2 is the inverse of the function 2 to the power of an exponent, then they'll cancel each other out and we'll just be left with what's on the inside, right? Because if you remember that property, and this comes handy all the time when you're doing calculus and other maths in university or college level, if you have a function and you're taking the inverse of the function as the input, well, you're just left with the input of that function, which is x. And the same thing goes the other way around. F inverse of f of x, same thing, right? So we're just left with what's on the inside there. So in this case, to do this, we take everything to the exponent of 2. Or I didn't phrase that right, but we'll have 2 to the exponent of what we've got on our left side, and then 2 to the exponent of what we've got on the right side. So we just said that since they're inverses, they'll cancel each other out, and we'll just be left with x over x minus 3 times the quantity 1 minus x. And then on the other side, we've got 2 to the power of 1 now. And all of a sudden, it looks a lot easier to work with. So it looks like we've done a fair amount of simplifying with only a couple steps right now. So what can we do next here? Okay, well, we can expand that polynomial in the numerator. So we got x minus x squared over x minus 3 is greater than 2. And so your mind might be going to two places right now. You might say, well, let's multiply everything by x minus 3. Let's get rid of the fraction. And you could do that. You know, math is still math, but you want to think what's going to be the easiest way. And I personally think that there's an easier way, and that is to keep this fraction. Because the thing is that when you multiply by x minus 3 on both sides, well, remember when we have variable terms and we're multiplying an inequality, remember we have to flip the sign if we're multiplying by a negative on both sides. But when we have a variable like x minus 3, we don't know if it's positive. We don't know if it's negative. So as soon as you multiply by x minus 3, you're going to have to consider, okay, when is x minus, if x minus 3 is positive, we're going to keep the sign the same of the inequality. But if it's negative, then we're going to have to flip the sign. So then all of a sudden now you've got multiple inequalities that you've got to solve. I think we're going to have to end up with multiple inequalities actually in this example anyways, but we're going to solve it a slightly different way. But yeah, I would say try that way as well if you want extra practice. So the other way, let's just move the rational function onto the other side, and let's simplify things down with algebra. And so if we subtract the left side from both sides, we get 0 is greater than, or sorry, 0 is less than, and we've got 2 minus x squared over x minus 3. Now let's just do some algebra. We've got now 2x minus 6 minus x plus x squared over x minus 3. Great. Okay. That was just multiplying the first term by x minus 3. We can simplify this now. We've got 2x minus x is plus x, so we've got x squared plus x minus 6 over x minus 3. Okay. And we can factor this as well. X squared plus x minus 6. Well, that leaves us with x plus 3 times x minus 2. And I'm assuming that you're able to do some basic factoring here. Great. So we're left with this. And this is a lot easier to solve. So when we're looking at this, we have an expression that says that this rational function is greater than 0. And the things that you need to consider here is that, well, a rational, like a fraction can be positive or greater than 0 when the numerator is positive and the denominator is positive, or when the numerator is negative and the denominator is also negative, right? Because a negative divided by a negative, it's going to result in a positive number, right? So we just need to remember that there's those two cases there. And I personally like to visually look at this. So if we've got, let's just graph the quadratic on the numerator. So we know that there's going to be roots at -3 and +2. And we know that it's a positive first term, so it's going to be like the second degree term is positive, so it's going to be shaped like this, right? So this is the numerator, and then let's draw the denominator. We've got x minus 3, so that's very clearly just a line with a slope of 1 that's shifted to the right by 3 units. So now we've got a 3 here, and let's draw that as well. Let's draw it like here. Yeah, and we know that it's going to look something like that. Okay, and remember what we said earlier. If they're both negative, remember this red function represents the numerator. The green function represents the denominator. So they both need to be either negative or they both need to be positive to satisfy the inequality. So we've got two regions that satisfy the inequality here. You can see that they're both negative on this region from -3 to 2. And then there's one more, which is a little bit hard to see from the scale that I've drawn this at. But if we extend this quadratic all the way up, something like that, then you should be able to see as well that they're both positive once x is greater than 3, right? In this region here. So that leaves us with, let's scroll down here, that leaves us with x must be, and we'll use set builder notation, or actually, I don't know if that's the right word. I'm not sure. I'll have to look that up after. From -3 to 2. And remember, since that our inequality is not inclusive, then we have round brackets here. If it was equal to, and that's okay, then we would use square brackets. So we've got from -3 to 2's, and then we've got the union of that domain with 3 to infinity. 3 to, and infinity will get a round bracket because we can never really be equal to infinity. Okay, so we got this solution, but unfortunately, this is not where the question will end. We need to look back at our inequality and try to consider something else here. And I encourage you to pause the video, try to think about what we haven't considered and why that first solution that we get would not be the correct answer. So assuming that you've thought that through, what we have to consider is that the logarithms have a domain of themselves, right? So we've got x over x minus 3 has to be greater than 0, and 1 minus x also has to be greater than 0. Because remember, when we look back at the definition of logarithms, we know that we can never end up with something like something to the exponent of a number is never going to be something that is negative, right? Even if you put in a negative exponent, that's just going to make the result a really small number. It's going to be 1 divided by that number now, right? So we're never able to achieve negative, which is why the inside of those logarithms has to be greater than 0. If that doesn't make sense, then I would go look back at like definitions of logarithms and maybe check out some other resources on those. So we got x over x minus 3 has to be greater than 0, and it has to be both, right? X minus 1 has to be greater than 0. There's x minus 1. Oh, no, 1 minus x. Good thing I checked. 1 minus x. The one on the right, super easy to solve. Let's do that now. We've got x has to be less than 1, right? Just move the x to the other side and we get x is less than 1. So x has to be less than 1. We know that that is a domain that this has to satisfy. Now let's look at the other one, x over x minus 3. And recall that when we had that rational function inequality in the just this previous step, we look at the numerator and then we looked at the denominator and we saw when are they both positive or when are they both negative. So let's do the same thing. Okay, well, and I always like to graph things. We've got, okay, x here. So this is the numerator. And then we've got green as our denominator. Okay, so this has an intercept at 0. And then x minus 3 will have an intercept at 3. And they're going to have the same slope, right? So you can see here that they're both going to be negative when x is less than 0, right? And they're both going to be positive when x is greater than 3. So those are our two regions. Okay. So let's draw a number line here. I'm going to draw a number line because remember, these two highlighted areas satisfy this inequality, but they need to also satisfy this inequality, right? So x has to be less than 1. Actually, it's probably easier without a number line. I think that might make things a little blurry. Oh, so let's draw number 1 on this number line. And we're going to use the color blue just to represent the region. So x has to be less than 1, right? Which means that x has to be in this region here, right? So you can see that what satisfies the solutions that satisfy all of these conditions are just these ones, right? When x is between negative infinity and 0, right? So we get x must be between negative infinity and 0. So this is just the solutions to the restriction on the logarithms domain. We haven't actually, like, this, it's kind of confusing because we got two separate answers, right? We had this answer, and this was the answer that actually was just the solution to our expression, our inequality with the logarithms. And then we got a completely different solution set for the domain on the logarithms. So the answer would actually be when you take the strictest domain of these two domains. So now let's draw a large number line. And we've got from -3 to 2 and from 3 to infinity. So let's just look at our critical numbers. -3, 2, 3, and 0. So we've got -3, and this is obviously not to scale. -3, 0, 2, and 3. Okay, and we've got from our first solution of the logarithms, we have from -3 to 2 and from 3 to infinity. So we've got from -3 to 2 and from 3 to infinity. So this red just represents what the logarithm solution. Okay. Let's write that as the inequality from question. I think that's a little bit more clear. And then the restriction on the logarithms domain, we found that x has to be from negative infinity to 0. So from this, we've got this right here. Domain on logarithm. Great. So now we can take the strictest domain, and I'm going to highlight that, and you can see that the overlap is just between these points here. So finally, we can conclude that x has to be between -3 and 0. And you can graph this yourself on Desmos. Like if you graph this, I would say move this to the other side, and then you'll get 0, and then treat 1 minus log of that thing minus the log of this thing. If you graph that as a function, you'll see that, because that'll be, here, let me actually write this out. If you have this is the exact same thing, right, greater than 0. If you graph that function on the right side, you'll see that is only greater than 0, or its positive value, when x is between -3 and 0. So that's just a quick way of checking that you made sure that your algebra was correct.